is Amodonkar, and today we are going to have this particular webinar where I'm going to show you some of the nice things in SolidCAM, in both in 3D as well as in the 5-axis side. What we are going to do is we are actually going to take this and I'm going to run you first through all the design features that we have done on this part, so that you can get an idea on how we are going to hold this part first of all, because in an aerospace component you are not allowed to do from casting or anything. It has to be from a single solid block. Now, a part like this, which is about 500-600 millimeter long, cannot be held in a vise. So you need some kind of a holding arrangement for this particular part. So we will create what we call as the lugs to hold this particular part, and we are going to hold that part. Sorry. We're going to hold the part using the lugs and some screws onto another holding plate. That holding plate will then. So this is more simpler. I'm going to run through the first 8 and other things, which will give you an idea on how to machine this particular part, how to first of all hold this part. Okay, what we are going to do now is I'm just going to run you through the steps, because I'm not going to create those steps again with you. Okay. So okay, from here we actually created, once we had the part, we created the lugs. We'll move it down, and you will see that we have got lugs up here that are getting created. So I'll keep showing you the lugs. The holding lugs that let's here. Counter bore, where we created the counter bore to seat an M8 screw into that. So this entire block will be then screwed down to the plate below. Another one, and if I switch on, then this is how the entire lug. Find the stock. We define the stock as a part of this particular stock. Now, if I switch on the CAD data and all of the lugs, you will see that the stock also has a counter bore. So I'm going to put an M8 screw in all of these holes and tighten this plate down onto the holding plate. Now this holding plate has a couple of other features. This holding plate will also have a pneumatic holding. It will be holding using vacuum. So we have got about 7 to 8 screws, first of all, holding the block down on the part. And the entire thing is then being held on the bottom plate, and then there's a vacuum that's actually holding the whole thing down, so that there are no warpages as such on this particular part. Okay, Having said that, I've got the lugs and the main part. Right, let's switch off the holding plate because we don't need to see it right now. And we will take this entire thing to machining. If you observe, my rib faces are all having a different color. And I'm going to show you one of the strong features of SolidCAM in selecting a geometry. Okay, so let me start a new milling. Okay, let's save it. External, okay. Let me select. So we're going to use today a machine from Spain called as Bermac, and it has a Siemens controller 840D. So I'm going to select that control, and the machine is automatically selected. Coordinate system, of course we're going to have one coordinate system. Just select one of these faces. I need it to the center, top center. Okay, I'll reselect the face. I'll flip around Z a couple of times. I want the X in this direction. Up here, 150, 25. So the thickness of the part is about 16 millimeters, so about minus 16.1. That's the height of the part. Okay. And now I'll go to my iMachining database because we're going to use iMachining in this to rough out majority of the area. I have different Bermac machine. It's a head type GP machine, so we have a minimum of 12,000 on the machine, a maximum feed rate of about 12 meters, and a spindle power of about 22 kilowatts. So it's a pretty heavy machine. Okay, and in the material database, I'm going to use an aluminum 6061 T6, the aerospace grade aluminum. Let me save and exit, select the machine, and the material. Okay. If you realize I did not define the stock because I want to open up the the stock using the model. So I'm going to switch on the stock up here, and in the stock it has already selected so many solids, which is unnecessary. My stock is only defined as solid. Okay, my stock is defined, so if I run the 3D, I've got the stock ready up here. Okay. Right, so let me switch off the stock. If I go into my target, I've got too many things. Again, I'm going to unselect all of them. Only inside my target, the lugs are also my target. So all the modifications to the data. So this is my target. Okay. Now I'm going to start with the first operation. My first operation is first to open up the outer area. And mind you that I don't have to not cut the lugs because the lugs are the ones that are actually holding. Lugs are part of my target, but not the main target, but the target for machining. So what I'm going to do is I'm going to add a 3D iMachining. We will just switch on the stock because I will be needing the contours. Okay, and I'm not going to use target up here. I'll say new, and okay, moment, let me switch off the stock. I'll select. I'm going to have to select the main part and the lugs. We are creating a a local target inside this particular operation, which will only be used for this operation. So I don't have to really change my original target that was defined, and also this surface. So wherever I need all of them together, I can select this model. Okay. Tool, since I'm going to remove bulk of material and I have got good power on my spindle, I'm going to use not a bull nose, I'm going to use a 20 millimeter end mill. Out of folder 55, cutting length is about 35, and it's a 3-foot holder. Eye data, I'm going to use a 45-degree helix, and HSK 32 by 80, that's the holder. Okay, so that's how my tool is going to look like. Levels, safety distance of 10 millimeter. Upper level is, let's make it 5. My upper level is 0, lower level is 16.1. Technology wizard, we are at level 6. We're going to have a 15.2 as my depth of cut, 15.7. That would give me an RPM of 4,607 and a feed rate of about 2.1 meter. Okay, we're not much worried about it. We'll keep about 0.8 stock for my finishing. And of course, in the toolpath parameters, I'm going to change the tolerance to a 0.1. Okay, that's all I need to do. I'm going to save this. Right click, calculate it. This would take about 10, 15, about 30 seconds, so you'll have to be a bit patient. Sorry, I made a small mistake. I'll probably have to come out of this, and because I don't want the entire part to be done. I just want only the exterior of this portion to be done. Just wait for the canceling to proceed. Okay, I'll just again switch on my stock. Sorry for that. Let's edit this operation. And in the geometry, I'll define the working area. This is what I missed. So that's the first outer one. And to select the inner one, I'm going to change it to wireframe and select the inner geometry. Auto constant Z. Yep. The first chain is open. That's okay. Okay, and I'm going to save this. Let's switch off the stock again now. So I don't need it anymore. And calculate the toolpath. Okay, it's done the calculation. Let's look at how the toolpath looks like. Let's switch on. Great. So we are going to only machine the outside first. So you can see that it has taken the lugs into consideration. So if I run the simulation, go into Solid Verify. Let's run it. That's nicely done. So we have got our first initial rough. And this was precisely the reason why we made the lugs, because when we do the outside operation, we should not lose the part. It should not become loose, because we don't have any other way to hold it. But there is a way that we have used. We have used a vacuum table. So it's actually, the vacuum is holding the part, but not good enough for us to be very aggressive in our cut. That is the reason we created this lugs, and we are holding on these lugs with about 8 M8 screws. Right, so we have done the external. Now, the very next operation cannot be opening up these pockets. The very next operation, if I open up these pockets, I'm going to be in big trouble, because I have these ribs, and these ribs can cause a lot of problem for me later on when I try to rough it, because they are just about 2 millimeter thick. So it can create a lot of vibrations. They can break. They can damage the tool. So the work here is to first rough only the ribs area and finish only the ribs area. Now this is a big issue, because there are so many different profiles, different heights, and we need to use a different kind of an approach for machining. What I'm going to do is I'm going to use the HSM and HSR strategy, where we are going to use a nice new function inside the geometry selection. Okay, so I'm going to add HSR. I will use, by the way, we are going to use now, you can use either the target or you could use the model, because I'm more interested now only in the rib area. I'm not interested in the lugs, because even if the lugs are not selected, that's good enough. So I'm going to select only the target. I will define a new ball nose cutter, diameter 10, 50 millimeter outside, 25 cutting length, 2 flute, same holder. Okay, the constraint boundary. Now this is where I'll have to be a bit careful, of course. Let's create ball nose, 10 millimeter, 50, 25, 2 holder, HSK. Let's select this. Okay. And the constraint boundary is, I just want to machine the ribs. Now, I have to generate the boundary only for the rib area, a major task. But we're going to use some nice function inside HSR, where we'll create this boundary manually by selected faces. Now, how am I going to select only the rib faces? And this is where the new function in geometry selection comes into picture. So I'm going to select the drive surface new. I don't want to keep selecting everything manually, so what I'm going to do is I'm going to pick a color from the model. I'll say this color. It has recorded the RGB value, the red, green, blue value, and I'll click on Find Faces. So it has selected 66 faces very quickly just by the color. So new feature, very helpful when you want to pick so many different faces with the same color. It's very fast. So I'm going to accept this. I'll give an offset of about 1.5 so that it's increased by 1.5 the area. Okay, and we'll calculate the boundary. Right, if I say show, you can see that so nicely the boundary has been calculated by the HSR function. Perfect. So let's say OK. Let's go to the process. I'm going to keep about 0.5 millimeter for finishing. Now why am I doing it now is because I still have a solid block. So I can be really aggressive in my cut. I can get a very nice surface quality because I have not opened any pocket. So it'll be very safe. A tolerance of 0.1, a step over minimum of 2, and a maximum of 3.6. I'm going to refine the corners. Adaptive step down, none. I'll go to the link. Okay, ramping. I'm going to give a 5-degree ramp, 1 millimeter height offset, more equal to the step down. Profile ramping. Retract minimum, and I'm going to clear the surface by 10 millimeters at least, so that I'd be safe. Leads are my default, save, and this is being calculated. This should take about 10 seconds. It's going to be pretty quick. Yeah. So if I show you the toolpath, this is how the toolpath looks like. Only the rib tops are being done. So if I now run the simulation, solid verify, so we'll have the updated stock from the previous operation. Okay, and let's run the simulation. As you can see, we're just cutting the ribs, nothing else. Right, so just the ribs have been roughed out, and we will now finish the ribs so that we don't leave anything to chance. So we will add another HSM toolpath, and I'm going to use the 3D constant step over. Use the same tool, ball nose. The drive boundaries are the same. The constraint boundaries cannot be a different boundary. It has to be the same, else it's going to machine everything else. So let's redo the boundary. Define, color, pick from the model, find faces, 6 to 6 faces again. Okay. And I'm just going to give 1 millimeter as an offset, not the 0.5. Accept. Okay, that's done. In the passes, I'll be about 0.5 up and down. Basically, that should do. Profile ramping, retracts minimum with 10 millimeter retract up. Leads, everything else default. Let's save and run the calculation. Again, this would take about 20-30 seconds. Okay, the calculation is almost done. Let's generate the toolpath preview. This is how it's going to look like. So we are finishing the rib tops. We are not leaving it to the end, because in the end we won't have any really strong material to cut this ribs. That's the reason we are doing that. Now what we have to do is, we have done with the ribs, we have done with the roughing of the outer edge. Now we will rough the inside. And again, I'm going to use iMachining 3D. We will use a different tool now. I'm going to add a bull nose, 20 or 1.5, because I have a radius of 1.5 below. Okay, 55, 35, 3 flute, holder, HSK, levels, 5, technology wizard, 6, technology. I'm going to keep about 1 millimeter offset, because I don't want the roughing to remove most of the material, because there could be a chance of a warpage seeping inside. In fact, 1 is less. We should keep it slightly more, so that we can remove the material in a couple of passes in swarfing, but that's okay. Toolpath tolerance, since we are going to be leaving that much material, I'm going to keep a tolerance of about 0.2. Link is all constant. We are going to use level 6 for our cutting. I'm going to save this. Let me just check the geometry. It can't be the target. Let's make it the model, because if if I keep it as a target, the software is going to remove these lugs because it's going to recognize them as additional stock. So that's the reason I'm using the model as my stock. We have two stocks. One was a local stock that I defined for my earlier operation, and I'm using the same thing for this. So right click and calculate. This would be slightly a lengthier operation because it involves a lot of cutting. So this could take anywhere between 2 to 2.5 minutes. Okay, the calculation is done. It's generating a preview. Okay, this is how my toolpath looks like. Very neat. It's only done the inside because we already know that the exterior has already been roughed out, so it doesn't have to touch the exterior. Let's run the simulation now and Solid Verify. Okay, this is how my part looks, the stock looks before the iMachining is about to start. It's very fast. Okay, that's almost done. Of course, there are some pockets which it has not entered. For example, it has not entered this pocket. It has left a lot of material here. That's pretty much obvious because we have used a much bigger diameter of the tool, but we are not much bothered on that because we always know that we can remove that material using a rest-rough function inside iMachining 3D. Right. What we are more interested to do now is to run a couple of Swarfing toolpaths because that's where we have the interest, and also how we are going to take care of the floor machining. So let me switch off this toolpath. So now what we have is we have this area up here which has got a nice draft. So it has got both positive as well as negative drafts. So let's pick that area, maybe a couple of pockets. We can pick two straight walls also and generate the toolpath. So I'm going to add the swarf machining. And since it's just 16 millimeters, I'm going to use a much smaller tool. So I'm going to jump onto the geometry, the swarfing surfaces. So I just need to select the surfaces for swarfing. These are the surfaces for swarfing. And this one. Okay. Let me show the direction. Okay. That's all selected. Right. Floor surface is very important because I don't want the tool to gouge onto the floor, so it's going to be this surface, and also the fillets accompanying the surface. So we'll select also the portions of the fillet. Okay, and this one. Perfect. Let's define a new tool. We're going to have an 8 millimeter ball nose, short tool. Not 80, sorry, it's 8. Total height is 70, outer folder is only 45, and a cutting length of 25 millimeter, 2 flute. I think this is too much, 60 is perfect. Holder, HSK. Okay, let's go to the levels. Put 10 millimeter as our entry and exit safety distance, the toolpath parameter. We can either use the side as auto detect, or we know that we have to do the inside machining, so we can select inside. Tool axis control, we will check the result, and if need be, then only we will change some values out here. Link, of course, I want entry and exit links, 1 millimeter above. And also for the lead out, 1 millimeter above. Okay, no gouge check necessary at the moment. Let's check the very first toolpath what we get. The best part of swarf machining is not much of definitions are needed, because it does the toolpath calculation almost automatically by itself. So if I take a visual simulation on the host CAD and see how this whole thing looks like. You can see the tool coming up. There's an entry, moving around the corner. And as it goes near to this the negative surface, you can see that the tool has already started tilting to get to that particular surface angle. It doesn't do the tilting up here, because if it does that, then you're going to have a very bad surface finish. Okay. So we do have issues in the corners. So what we're going to do is we're going to first change that. Let's fix that issue. That issue we can fix in the tool axis control, and I'm going to click on minimize rotation axis changes. So we will minimize the rotation and run the calculation. Let's run the simulation now. And we can see that it maneuvers on the corner much smoothly. The only hitch being that it will adjust its angle almost on a very small area. This is another issue that we need to take care of, okay, which is not a major issue at the moment. We know where the problem is. So what we're going to do is we'll just create a simple 3D sketch up here and draw a line joining that. So I'll just create a couple of lines so that the tool doesn't lose its orientation up here. This probably can happen because of some geometry issues, but what is more important is, do we have a solution? Yes, we do have a remedy for that. I'm going to edit, and in the geometry, I'm going to select some tilt lines. Okay, so you have one. Reverse, please. Yes. 2, reverse, yes, 3, reverse, okay, and the edge, okay. So I have to keep selecting my tilt lines. That's hardly some work. Okay, let's select this one, reverse, this one, reverse, okay, and this one up here, and this one up here. All right, so that's all. Those are my tilt curves. Okay, let's run the calculation. Save and calculate. Let's run the simulation now. It looks much better. Okay, that's how my tool is going to approach, maneuver the corner, tilt, and you can see that that problem we just sorted out. The tool completely trying to sleep, sort of sleep on the part, and we have done it very neatly. So the solution is, if sometimes because of geometry you have an issue that the tool is trying to dance its way around, there are two easy things that you can do. First is to lock up the rotating angle, so that takes care of the corner jerks. And then when the tool is trying to sleep, because probably the ISO lines of the surface are sleep on them, in such case, locally you could identify and create immediately, within a couple of seconds, you can create this sketch and use this lines to guide the tool in that problematic area. Right, so what we have now is we have a single tool path. However, this is not good enough because we have left, you remember, a millimeter of material on the wall. So what I'm going to do is I'm going to go into roughing and more, and I'll say I want 4 layers of 0.25 millimeter each, so that I'm going to enter slowly into the wall 0.25, 0.25, 0.25, 0.25, so that I clear that material. And the link between passes, it should be blending. It should blend a spline. Let's save and calculate. Okay, that's done. Let's look at how the tool path looks like. You can see that we've got few passes up here, more than what would be needed. So we are going to take multiple passes into the material. All right. Now, once we have done the swarfing, now what is the advantage of swarfing? Why did we do swarfing? If we did not do swarfing, we had the other way of doing it in 3-axis, and that was to use a disc cutter and go around this entire path several times. Take depth of cut. Let's say even if you had taken 0.5 as a depth of cut, we would have got about 32 passes. And if each of this pass takes about, let's say, 1 minute, so to machine one pocket, we would have taken about 30 minutes. Compare that with swarfing. Each pass takes about less than a minute to go around this pocket. We have 4 passes, so it takes 4 minutes. So we're dropping down the machining time almost by 70–80% using swarfing. And the other best thing about swarfing is that it gives you an exceptionally high surface finish on the side walls. The surface quality is much better. Okay, now we have done the wall and some area of the bottom floor surface, but the majority of the floor surface is still remaining. So what we are going to do is we are going to create another 5-axis tool path very quickly. So I'm going to add Sim 5X, parallel to curve, and the geometry, I'm going to machine this surface. The edge curve is that with constant Z. Okay. Number of cuts, we're going to keep about 20 cuts. Tool, I'm going to use the same tool, ball nose, 10 and 10. Okay. Tool path parameter, we're going to keep about 0.7 millimeter. Step over between both of them. and it's going to be a zigzag, spiral kind of machining, not zigzag. Tool access control, I'm not changing anything here, but what we are more interested is the gouge check. So I'm going to enable the gouge check, tool shaft, arbor, and the tooltip. This is to be checked against these surfaces that were finished with swarfing. Okay, and what it has to do when it comes to such area. What is the gouge check that we're going to use? We're going to use tilting along tool. We have to tilt the tool, but we're going to use a new mechanism in tilting. All these days we had side tilt, and lead lag, but we have a new feature, and that's called automatic. The software will decide whether to apply a lead lag angle or a side tilt angle or a combination of both. If only a tilt angle is needed, it will not apply the lead lag, it will only use the side tilt. But if there is a region which needs a combination, then it will apply both of them. And all this is possible in a single toolpath. Okay, so we're going to keep about 0.1 millimeter away from the surface because I don't want to touch the surface. Okay, let's save and calculate. Look at the toolpath. Okay, that's too much. Let's reduce it because 20 cuts are too much. Let's bring it down to about 12 of them. Okay, right. So what we're going to do now is just run the simulation and see how the tool behaves. Up till here, it has no gouge. The problem will start. See, the moment it starts now coming closer and closer to the surface, it will start tilting. It's going to use only the tilt mechanism here because it doesn't need the lead lag. They're not needed up here. You can see that it's nicely tilted it to avoid gouging. So this is a new feature inside SolidCAM 2014 in tilting. It's called as automatic. It will use a combination of lead lag and side tilt in several places. It's not that it's always going to use lead lag and side tilt. It will use either lead lag or side tilt or a combination of both of them to come in one single toolpath. Okay, that also is done. Now what remains is the center portion because we still have about 0.5 to 1 millimeter material on this wall. So it's pretty simple. I'm going to add a pocketing function. I'll pick the tool. We will use the 20R 1.5. Select that. The upper level I'm going to pick here, and I'll give a delta value to this. That's about 1. Pocket depth is this one, so it's 1 millimeter. Technology, an offset of about 3 millimeters or even more. 4. Okay, and in the link we'll use the helical ramping. Let's save and calculate. Oops, sorry, the geometry. Out of constant Z. Yes. Save and calculate. Yep. So we have just a single toolpath. That should take care of the majority area. So we have this toolpath and this one. Both of them will overlap, so we won't leave any material on the bottom. So what we did now was simple. We created a swarfing, then we created a parallel to curve toolpath with auto tilt to remove that material that comes from the wall onto the bottom area, and then the remaining one we generated a pocketing function. Let's apply the same thing to this side. Let's see one more pocket on how we are going to achieve that. So let me add the swarf machining geometry. So my swarfing is going to be this one up here. These are the surfaces. Okay, floor, of course. 1, 2, 3. I'm sorry, not that one. That's one. The fillets and the bottom surface. That's all we'll need to be selected. Okay, the tool that we're going to use. Remember, the tilt lines are not necessary. They are only necessary when you start getting into really tight situations. So it's not absolutely necessary to have it. Okay, inside tool axis control. Of course, we're going to use a minimum rotation axis change. Link, lead in, lead out with 1 millimeter height. As you can see, creating a swarfing toolpath is very simple, very fast on the machine too. So you don't need to spend a lot of time. The toolpath creation is also pretty quick. So if you run the simulation now, so we have a problem here. That's the side, the issue with the side. Let's go to the toolpath parameters. It should have been inside. I picked outside by mistake. Save and calculate. Run the simulation. Okay. Very nice. Very nice. You can see that it can be all done in just one single toolpath. You don't need multiple passes to generate this toolpath. So we will again apply roughing 4 layers of 0.25 and calculate it. Run the simulation. So we've got several of these toolpaths. So what it's basically doing now is it's going around the part and slowly taking a radial step over. It's taken the radial step over and it's created this nice toolpath. So what you have is a nice passes. It's taking the material from the side walls slowly and as it enters into the material. So the biggest advantage of swarfing is that you could generate the toolpath very quickly, and on the machine it can just run as quickly as it was generated to give you a very nice surface finish on the wall without having to take multiple depths. Now it's not that you cannot take multiple depths in swarfing, it's simply possible. So instead of layers, I'm going to say 1 layer. I can say number of slices. So my number of slices, I can say 10. Okay. I can either morph the pattern or step from top or step from bottom. So I'm going to morph the pattern, 10 slices. Let's save and calculate. Okay, that's also done. This is how my toolpath will look like. You can see how nicely it has morphed it. It's morphed, starts from up, goes all the way down. But honestly, if you would like to do swarfing, it's always best to be done using a single pass, so that you can use the full flute length and generate an excellent surface finish on the sides. Using the same method, we can actually complete the entire part. You don't need to do constant Z kind of machining. You can just take single passes all over. But of course, since you have left a lot of material on the side walls, you have to take several passes, maybe 4 or 5 passes radially into the material. It's also very easy on the material. Not much of stresses are generated when you go in this method. So overall, you will get a much better part, much better surface, and extremely low machining time. What we're now going to do is probably pick up a few of these toolpaths, and let's add the setup, machine setup. Okay, let's switch on the holding plate so that we can define the fixture, the holding fixture, and let's put a Z value of about 55 millimeter. Okay, and take a couple of swarfing toolpaths. simulate, and go into the machine simulation. So we have this Burmac machine, which is a head-head type of machine, a gantry type, wherein you can actually put large parts because the bed is pretty huge. Okay, so the machine looks something like this. So it's a pretty huge machine. It's a gantry type, head-head, and we have the holding plate and the part mounted on it. Of course, the stock, I would like to make it opaque, and I'll hide the part, so I just have the stock. Also, I'll hide the frame of the machine, so that going to make it a bit easy for me. And I'm going to run the toolpath. So you can have a look at how the machining happens. This was the okay, let's stop this, go to the move and go to the next one. It's pretty quick. I can move between toolpaths. Very nice. You can see as it goes to the end, it's automatically doing the, oops, we had a problem. We need to check that toolpath. We need to check why it created. It's because of the number of passes. That was a problem. Let's edit and reduce the number of passes. Geometry, let's say 10 or even 8. Save and calculate. Okay, that's okay. And then we have this toolpath for machining the floor, and of course we also saw this area up here. So if I have to run only this, let me go to the settings, switch off the verification and run the simulation of this fellow. Okay, let's switch off the machine. Let's have the toolpath and the tool. That's how my machine is going to run. Sorry. Very quickly, this is how it will run. Okay. Now, since this is a Siemens machine, I'll also show you the output coming out from the software. Let's generate the G code. Okay. So we have got Siemens output coming up using the RTCP function, Trauri. Okay, and as it goes down, you can see that we're using the vector output to Siemens. Siemens will do the calculation for me. We use the A3B3C3 function. Okay, that's here. So effectively, this is how my toolpath would look like. If there are any questions, I'd be more than open to answer your questions. You can either type in the chat bar or just raise your hand and I'll give you an opportunity to ask questions. If there are no questions, then it was nice having you on the webinar. If you still have questions, you could always write to us on our email address and we'll be more than glad to help you. I see that there are no questions. You obviously will also have an opportunity to write to us if there are questions, and we will be more than glad to answer it. Thank you very much for attending this webinar, and have a nice weekend.